Welcome back. So now that we have discussed what the properties of acids and bases are and what it means in terms of what happens to a solution when we add an acid to a base to it, we're going to look at the different theories of acids and bases. The main theory that we look at for VCE chemistry is called the Bronsted-Lowry Theory, and that's the one we're going to define in detail. There are other theories of acids and bases, but we don't look at them in detail in VCE. So when we talk about defining acids and bases, we have usually in junior science looked at acids being something that causes the pH to go down below 7. Okay, so the pH is going to be lower than 7 if it's an acid, and if it is a base, then the pH will go up. Okay, the more basic it gets, because the pH greater than 7 is a base. So typically we have looked at acids and bases purely by looking at their pH, and this actually links to a theory of acids and bases called the Arrhenius theory, where something that increases the concentration of H+ in solution is an acid. So while we didn't name this theory of acids and bases in junior science, that's really the one we've looked at. There is another theory of acids and bases called Lewis acids and bases, which we won't look at all in VCE, but what we're going to look at is the idea of the Bronsted-Lowry theory. So the Bronsted-Lowry theory allowed us to look at acids and bases in things other than just solution. So if it increased H+ in solution, that was the only way we could define an acid before, and we do know that we have some acidic gases and things like that. It allowed us to be able to define metal oxides as having basic properties or acidic properties and things like that. So the key definitions that we need to know for the Bronsted-Lowry is that we define an acid as a substance that can donate, give up, a proton being a H+, so a hydrogen atom that has lost its electron, leaving behind essentially a proton, because if you remember, a hydrogen consists of one proton and one electron. So if we lose the electron from a hydrogen atom, we are left with a proton, and we show that as being H+. This will increase the overall hydronium ions in solution, because as the acid gives up its proton, that proton will then react with water, forming H3O+. A base is the opposite. So we define a base as any substance that will accept a proton, so the proton coming in, which reduces the hydronium ion concentration, because if you think that extra proton has got to come off a hydronium, when it does, it reforms water and it decreases the hydronium ion concentration, therefore increasing the hydroxide ion concentration, or the relative concentration of these. So the key things that we need to remember is that an acid and base reaction must involve the transfer of hydrogen ions from one species to another. So we need to see a hydrogen atom swapping from the proton donor to the proton acceptor, so from the acid to the base. So a substance cannot act as an acid or base without a base present, because we cannot transfer that hydrogen from the acid unless there is a base ready to be there to accept it. This is much like how we defined ionic bonding, where we said that an electron won't leave a neutral atom to form a positive ion unless there is a nonmetal atom to accept that negative electron and form a negative ion. So with ion formation, when we form ionic bonds, we have to have the transfer from one to the other. And with acid and base reactions, we are now talking about the transfer of a hydrogen atom. Or more to the point, a hydrogen ion. So the Bronsted-Lowry principle allows reactions in aqueous solutions to occur, and for us to identify the acid and the base. We have a look here, we have HCl, and we can see that on this side here we have Cl-. It has lost a H+, which means that it must have donated its H+ to something else. And if we have a look at the water here goes from H2O to H3O plus. It has gained a H plus. So in this case, HCl is donating, is the donor, so it is the acid, and H2O is accepting, so it is the base. And in order for an acid-base reaction to occur, we must have a donor and an acceptor. Okay, so by definition, the donor is the acid and the acceptor is the base. So a Bronsted-Lowry acid must have at least one acidic proton. Okay, so when we talk H3PO4, we actually have 3 acidic protons. If we're talking ethanoic acid, okay, the protons on the methyl group here are not acidic. Okay, they are too strongly held in these largely non-covalent, non-polar covalent bonds, but this highly polarized bond here is the one that will ionize. Okay, so this one here is our acidic proton. So when we look at things with carboxylic acids, it is only the hydrogen of the carboxylic acid group which is acidic. Okay, so we need to have a highly polarized covalent bond which will readily ionize when it's placed into water. Our acids can be classified as monoprotic, okay, which means it gives up one proton. And an example of that is hydrochloric acid or ethanoic acid. They can be diprotic, which means di being 2, they give up 2 protons, and an example of that would be sulfuric acid. Okay, or they can be polyprotic, where they give up 3 or more. Okay, and in this case, the phosphoric acid is triprotic or polyprotic. It has 3 acidic protons that it can donate into solution. Okay, so we can classify our acids as mono, di, or polyprotic based on the number of hydrogen ions that they will give up in solution, and therefore the number of hydronium ions they will form in water. So we can look at species that are considered to be Bronsted-Lowry acids or bases, going back to our common acids and bases. Okay, so substances that will dissociate or ionize into solution to form H+, such as nitric acid, hydrochloric acid, phosphoric acid, or sulfuric acid, are all considered acids according to Bronsted-Lowry acids and bases. They will donate that acidic proton. Acidic oxides are also acids. These are our NOx and SOx gases, so SO3, okay, and NO2 gases. These react with moisture in the atmosphere and form acids. So these are our sources of acid rain. Okay, so these are our nitrogen oxides, sulfur, and even carbon, because our carbon oxide, so carbon dioxide, reacts with water in the atmosphere to form carbonic acid, and these are massive contributors to acid rain and pollution in our atmosphere. Bases, on the other hand, are substances which will form bonds with the newly formed H+ ion, so they're acceptors. So that is carbonate anions, CO3 2-, so things such as limestone, hydrogen carbonates, HCO3 2-, these charges have moved, let's just move that, hydroxide ions, and oxides. All of these will react with acids and neutralize them. So substances with non-bonding pairs of electrons, so ammonia, okay, can form bases, okay, so if they're able to accept a proton. So we see that with the reaction of ammonia gas reacting with hydrochloric acid will form ammonium chloride. in this case, the ammonia accepts a proton forming NH4+, and this hydrogen chloride or hydrochloric acid loses the proton forming Cl-. These two ions will then react to form an ionic bond and will form ammonium chloride solid. Only in the gaseous state though, because if you remember your solubility rules, ammonium chloride, ammonium salts are always soluble. So if it's in aqueous solution, we won't see anything. It'll just all be soluble in solution. So when a Bronsted-Lowry base accepts a proton, the new bond formed is often a dative bond. That's a type of bonding we don't look at directly in VCE, and it involves the formation of a bond from a lone pair. If you want to know more about that, be sure to ask me in class. Okay, so I'm going to leave that here. That's our Bronsted-Lowry acid and base theory. You need to be able to define your acid and base according to Bronsted-Lowry theory and write equations for these. So good luck. Don't forget to take your notes, and I'll see you in class.